Here's how a spectrophotometer works. A lamp provides the source of light. The beam of light strikes the diffraction grating, which works like a prism and separates the light into its component wavelengths. The grating is rotated so that only a specific wavelength of light reaches the exit slit. Then the light interacts with the sample. From this point, the detector measures the transmittance and absorbance of the sample. Transmittance refers to the amount of light that passes completely through the sample and strikes the detector. Absorbance is a measurement of light that is absorbed by the sample. The detector senses the light being transmitted through the sample and converts this information into a digital display. Let's practice by performing a simple experiment. In this exercise, we'll determine the absorbance spectrum of red food coloring. To begin, set the wavelength to 380 nanometers. With the sample chamber empty and the lid closed, set the display to 0% transmittance by using the zero control knob. There are two cuvettes. One contains only millicu water. This is our blank. Wipe the blank cuvette with a Kim wipe to remove any fingerprints, and place the cuvette into the sample chamber by aligning the guide marks. Adjust the display to 100% transmittance. Remove the cuvette with the blank solution. Now set the display mode to absorbance by pressing the mode control key. The second cuvette contains millicu water and red food coloring. This is our sample. The absorbance of the sample is 0.845. Press the mode control key to select transmittance. The transmittance for the sample is 14.2%. Increase the wavelength by 25 nanometers to 405. Wipe the blank cuvette again and place it in the sample chamber. Adjust the transmittance control knob until it displays 100%. Now remove the blank. Wipe the sample cuvette and place it in the sample chamber. The transmittance for the sample at 405 nanometers is 7.4%. The absorbance for the sample is 1.130. Record this in your lab notebook. Increase the wavelength by 25 nanometers to 430. Repeat these steps with the blank and sample, writing each value in your lab notebook. Increase the wavelength by another 25 nanometers to 455 and test the sample again. By repeating these steps up to 680 nanometers, we can plot the absorbance spectrum for red food coloring. Now that we've finished our first practice exercise using the spectrophotometer, you're ready to enter the lab and try it for yourself.
The accuracy of the results of your titration will be a reflection of the care you took while performing it. When done carefully, titrations give very accurate, precise results. Here is a step-by-step procedure required for performing successful titrations. The burette has now been cleaned and prepared as shown in the previous videos. The meniscus is level with any graduation mark on the burette between 0 and 2 milliliters. The initial reading will be recorded, remembering to do it to 2 decimal places. The analyte solution is pipetted into the conical flask and then a few drops of the indicator is added. The conical flask is then placed under the burette. When performing the first titration, the solution is delivered at a rapid pace to get a rough idea what volume is needed to reach the endpoint. This is known as a rough titration, and it is not included in your final results as it is not accurate. However, you still need to record the final volume reading from the burette. The volume of solution delivered is determined by subtracting the final reading with the initial reading. The burette will then be refilled. Initial readings recorded and the solution in the conical flasks prepared in preparation for the next titration. The next titration will be done carefully to ensure that the endpoint is not missed using the volume recorded during the rough titration. The general procedure is to deliver approximately 3/4 of the volume of titrant recorded from the rough titration at a rapid pace and then add the titrant slowly until the endpoint. It is even possible to add a drop, swirl, add another drop, and so on until an endpoint is reached. When approaching the endpoint volume, a good habit is to wash the sides of the conical flask with distilled water from a wash bottle, as when swirling, the side of the conical flask will touch the tip and some of the titrant will stick to the walls of the flask. If there is a droplet hanging on the tip of the burette, wash the droplet into the flask using a wash bottle, especially when approaching the endpoint. Washing off the titrant will result in a more accurate and precise result. Once the endpoint is reached, the final reading is taken and the total volume of titrant delivered is determined by subtracting the final reading from the initial reading. Titrations are generally done in triplicate, so you will need to perform 2 more titrations. To get precise results, your volume of titrant delivered for the 3 non-rough titrations should be 0.1 milliliter difference between each titrant volume delivered. If this is not the case, additional titrations will be performed to get precise results. To better observe the color change of the indicator, a plain white piece of paper is placed under the conical flask. For right-handed individuals, the burette tap will be handled using your left hand, while the flask is swirled with the right hand. However, for left-handed individuals, the burette tap is handled with the right hand and the flask swirled using the left hand. In this case, the left-handed individuals will have to reverse the burette to accommodate their titrations. Here is the summarized procedure required for successful titration. Step 1. If the sample is a solid, it is weighed and then dissolved to make up a known volume of solution in a volumetric flask. Step 2. A pipette is used to measure accurately a volume of the solution, for example, 10.00 milliliters. This is emptied into a conical flask. Step 3. A few drops of an indicator may be added to the conical flask. This will show a change of color once we have reached the endpoint or when the titration is complete. The following indicators will be used in your practicals. Step 4. A second solution is placed in a burette. This is the titrant. This solution contains a chemical that will react with the analyte chemical sample in the conical flask. Step 5. The solution from the burette is run into the conical flask. The solution is added 1 drop at a time and swirled to mix the solutions as the endpoint is approached. Eventually, a color change shows the correct amount that has been added to react completely with the analyte chemical in the sample. Step 6. The volume of solution added from the burette is noted. The titration results can then be used to calculate concentration. Using the following steps ensures that your titration experiments are carried out using the correct techniques that enable you to get precise and accurate results.
Now let's get more familiar with the intricacies of the separatory funnel. As we can see here, the funnel has a stopper at the top and a stopcock at the bottom. This middle region is where our separation will take place. To get this ready, you might have to add a little bit of grease to the stopper and/or stopcock since they tend to get stuck. To set up for the extraction, we'll start with a ring stand attached to a support like this. We'll then place our separatory funnel in the ring and make sure everything is secure. To verify that the stopcock works, add some water. Make sure there are no leaks when the valve is closed. Open the valve to see how the water flows. Once satisfied, remove the water. We are now ready to get started. So let's say this is a reaction mixture that we just got from performing a chemical reaction in some organic solvent. Most of the time, you'll need to quench a reaction once it's finished by adding water. This means to stop a reaction mixture from reacting further, often with dilute weak acid or base to neutralize any ionic species. This means that after any chemical reaction, you will need to perform an extraction to separate your organic compounds from whatever is in the aqueous layer. In this particular case, rather than a reaction mixture, we simply have a mixture containing benzoic acid and 2-methoxynaphthalene dissolved in diethyl ether, and our goal is to obtain each of these two compounds in a pure form. These are both soluble in diethyl ether, but insoluble in water. However, if we add aqueous base to this mixture, benzoic acid will deprotonate, becoming the benzoate anion, which has a formal negative charge, and will thus become water-soluble and move into the aqueous phase. Since 2-methoxynaphthalene will not react, that will remain in the organic phase, and the two compounds will have separated. With our strategy understood, we can begin performing the technique. Making sure that the stopcock is closed, let's transfer our mixture to the separatory funnel using a conical glass funnel. This is our organic layer. To make sure we have transferred everything, rinse the beaker that held the mixture with ether and transfer that as well. Had this been the product of a chemical reaction, it would already have been quenched and thus have formed organic and aqueous layers. But since we are just doing an isolated extraction, let's go ahead and perform the necessary acid-base reaction right in the separatory funnel. To separate benzoic acid from the mixture, we will add 30 milliliters of 1 molar sodium hydroxide to the separatory funnel. This will pass through the organic layer, react with benzoic acid on the way to form sodium benzoate, and drag that down to the newly forming aqueous layer on the bottom. To make sure the reaction goes to completion, we need to mix the contents of the funnel. We will do this by inverting it and lightly swirling a few times, holding the stopper down with one finger as we do so to ensure that nothing spills out. Mix for about 10 seconds each time. After each round of mixing, hold the funnel upside down and open the stopcock like this to vent any gases that accumulate from the reaction. Close it and then continue mixing. When gases are vented, you will hear a brief hissing sound. When the sound no longer occurs, no more gas is being produced, and we can be confident that mixing is complete. After mixing, it is time to separate. Return your separatory funnel to the ring support and allow the contents to settle. You should see the two layers separate clearly. You can now open the stopcock to let the bottom layer drop into a clean flask. This is where you have to be careful. Watch the aqueous layer drip slowly so that you can stop it right before any of the top layer goes through. When the line separating the layers reaches the stopcock, close it. You have now separated the two layers. The top layer can be removed by pouring it through the top of the funnel into a separate flask. Be sure to pour it out the top and not through the stopcock, as pouring out the bottom would contaminate it. With most extractions, we will need to do more than one separation so as to maximize your yield, as not all of the benzoic acid made it out of the organic layer. So let's put this first aqueous extract to the side, return the organic layer to the separatory funnel, and make sure everything is secured. We can then add more aqueous base to the organic layer and mix just as we did before. Allow the layers to separate, and we can now collect the bottom layer again, adding it to the original extract. So now the extraction itself is complete. We have some aqueous sodium benzoate, and then we have 2-methoxynaphthalene still in the organic solvent. Let's isolate this first. The organic layer will likely contain residual water from the multiple washes that we performed. How do we get it out? We use a drying agent. A drying agent is a compound like sodium sulfate that removes water when added to a solution. The water should bind to the drying agent and thus join the solid phase. Keep adding the drying agent until you see a clear solution with all of the solid clumped at the bottom. You will know it's dry when lightly shaking the flask does not cause any solid to move around the solution. To separate the drying agent from the liquid, we'll need to do a gravity filtration. Since we discussed this at great length in the previous tutorial, we won't go over the details here, but set up your filtration and pour your dried organic layer in. The drying agent will remain on the filter paper, and the target molecule will move through with the solvent. Make sure to rinse the flask with more solvent so that everything is transferred. Then just evaporate the solvent on a hot plate, as ether is rather volatile, and we will be left with the residue of pure 2-methoxynaphthalene. The aqueous layer will be a bit trickier, as we wanted to isolate benzoic acid, but here we have sodium benzoate. To get benzoic acid, we will need to do another acid-base reaction to protonate the benzoate. Let's add about 5 milliliters of 6 molar hydrochloric acid. You may need to add a little more than this. Just monitor the solution with litmus paper and add it until the solution starts to turn acidic. A pH of around 2 means that the acid is no longer neutralizing base, but is turning the solution acidic, which means the acid is in excess and the reaction is complete. As benzoic acid forms, it will begin to precipitate. If this is happening very slowly, the flask can be placed in an ice bath or cold water bath to encourage solid formation. Once precipitation of benzoic acid is complete, it can be collected by vacuum filtration. Again, we have described this technique in the previous tutorial, so we will not go into detail here, but collect your solid on the Buchner funnel and allow it to dry on the bench for some time, then moving it to an oven if further drying is necessary. And with that, we have completed a liquid-liquid extraction. We had 2 organic molecules mixed together in an organic solvent, and we separated them based on their chemical properties, namely their propensity to undergo an acid-base reaction. This is an important tool that is used constantly in organic chemistry. It is also widely used in industry for the extraction of natural products, ranging from caffeine extraction from leaves to metal extraction from minerals. With this now understood, let's move forward and check out some other techniques.